It's our great pleasure to have our second lecturer, Professor Christophe Grojean. So, please, Christophe.
It's certainly a pleasure to be here. And so I would like to thank the organizer and also the DESY Foundation. So I think, the purpose of theoretical physics is always to push the frontier, and I think this foundation is here also to push the frontier of science. So that's certainly a unique moment in the history of physics, at least in Russia, right? So I've been asked actually to give you an introduction to the standard model and also maybe of physics beyond the standard model. So of course, physics beyond the standard model doesn't exist yet. So we have plenty of good ideas, and the rule of the game is actually to find out which of these nice ideas is actually correct and will describe nature.
Maybe it exists. We didn't find.
Right. So, first of all, I don't know exactly how many of you are theorists and experimentalists. So, I don't know, maybe the theorists can raise a hand. Okay. Good. And the other are doing some LHC experiment, or is there anything else beyond LHC? Good, so I will try to adjust the level of the lectures such that everybody can understand at least part of the lectures. But certainly if what I'm going to say is very well known by all of you, don't hesitate to stop me and say, okay, you can accelerate and skip some part, right? And then we can go into more details on other stuff. So I will focus mostly actually on the electric part of the standard model. So there is also the other part which is QCD, which is well known and well tested. Good description at the LHC. But I would say that maybe there have been not so many, improvement in the understanding of QCD. So people have been able to add, some higher order correction, but fundamentally there's nothing really new. While in the electric sector, there have been this discovery of the Higgs boson that's been a big change in our understanding of nature. Yes, right, absolutely. And Kevin, and certainly is much more an expert on QCD than. So for the electric theory, so everything started actually by the observation of beta decay. So beta decay is just the transformation of a neutron into a proton inside various nuclei. So for instance, you can take a potassium atom, potassium nuclei, with 19 protons and 40 nucleons in total, and this will spontaneously decay, for instance, into calcium, Ca plus, with 20 number of protons, or with the same number of nucleons, so nucleon is proton plus neutron, with the emission of with an electron. And there are various examples of this beta decay, right? For instance, you can have the copper that decay into zinc, plus again an electron, or you can also have simply hydrogen decaying into helium plus electron. So 1, 3, and 2, 3. So in all of this reaction, actually, you can really describe something like a nucleon decaying into a proton plus an electron. And of course, this is a two-body decay, right? Apparently, that's what was observed, right? And the funny thing is that people were looking actually at the number of events and plotted this number of events as a function of the energy of the electron. And what they noticed is that actually you have a spectrum like this with decays. But the funny thing somehow is that the energy of the electron is not fixed. While in principle, if you have a two-body decay, just by special relativity, the energy of the electron should be totally fixed by the mass of the neutron, the mass of the proton, and the mass of the electron. And this famous expression that you can derive is that the energy of the electron for a two-body decay will be the mass of the neutron squared minus the mass of the proton squared plus the mass of the electron squared divided by 2 the mass of the neutron. If you want to put the dimensions, you have to put c squared. So this was clearly in contradiction with the observation. Right? The energy of the electron is not fixed. And this relation is very powerful because you can really derive it only from special relativity. So it's purely kinematical relation. Doesn't depend at all on the interaction. So independently of the dynamics that really triggers this relation, just by imposing special relativity, this relation should hold. So that was quite puzzling at that time. People were saying, well, maybe energy is not conserved. Or maybe indeed, you have a violation of special relativity. Right? And at the end of the day, the explanation actually was much simpler than that. Right? You don't have to give up on kinematics. The only thing that you have to add is actually an extra particle. So actually, this beta decay is not a two-body decay, but it was assumed actually by Pauli in 1930 that there is an extra particle that appears into this decay. And you know that nowadays, this extra particle is nothing else than the neutrino or the antineutrino. In this case, now you have a free body decay, and free body decay, the energy of the particle are not fixed by the mass and can vary. There is only a maximum energy with the electron which is related to these things. So here the spectrum should end, right? And you can really notice experimentally that the end of the spectrum actually agrees very well with this relation. So now the question was actually what is the dynamics of this beta decay? So now we understand really the kinematics. So what is the dynamics? So what is the interaction that forces the neutron to decay into a proton? And that was what Fermi proposed in 32 or 34. In a very nice article that was actually rejected by Nature because it was found to be too speculative. So Fermi at that time, was trying to do the simplest thing he could do, simply add a 4 Fermi interaction. So you have 4 particles into this decay, and say, well, I will simply write actually an interaction among those 4 particles. Write simply a Lagrangian, which is constant, that he calls the Fermi constant. Somebody else calls the Fermi constant. For some reason that is still mysterious to me, people put a square root of 2. That I cannot understand. And then he simply describes those 4 particles by some spin of it. So, what is the notation? Psi for the neutron. Even though they are not, we know nowadays that they are not elementary particles, but you can still describe them by some Dirac field, if you want. And here, that's something that was not totally clear at that time, but nowadays we know actually that really the current associated to this Fermi decay is nothing else than gamma mu 1 minus gamma 5 over 2 psi proton. So that's the hadronic part of the current, and then there is a fermionic part. So this is product times the same thing for the neutrino, psi of the neutrino or the antineutrino, gamma mu 1 minus gamma 5 over 2 psi of the electron. And somehow this Lagrangian was simply built in analogy with QED, the QED interaction, where, for instance, you have 2 electrons, scattering of 2 electrons. You can exchange a photon. And you know that this scattering gives rise also, in a sense, to a 4 Fermi interaction via the exchange of the photon. You could write psi bar mu, gamma mu, psi e squared. And here, somehow, you will also have simply the propagator. Again, you write it better than eta mu nu, q squared plus I epsilon, psi bar mu, gamma nu. So that was simply QED, right? And from this, you can derive, for instance, the Rutherford formula for small scattering angle and all these things. So the idea then behind the Fermi interaction was simply to say, well, I will build something very equivalent, right? So some current-current interaction, right? This is a current, this is another current, so it's really the product of two currents. And here you can see simply this 4 Fermi interaction as an exchange of a new particle. And the difference compared to QED is that here in QED you have the exchange of a massless particle, the photon is a massless particle, but for the beta decay actually you have to introduce a massive particle that has been called later the W. So you will write simply here, you replace this current here, G mu. And you introduce a massive particle. So you have the mass of the particle, so Q squared minus mw squared plus I epsilon. And you have a new interaction, GW. So clearly, if you are at low energy or small momentum transfer, you can neglect the momentum here compared to the mass of the particle, and you will simply reproduce actually the 4 Fermi interaction. With the identification that G Fermi, you can predict G Fermi is square root of 2, is simply, it will be the square because you have 2 gauge coupling, GW squared divided by the mass of the W. So from beta decay, this is the only quantity that you have access to, right? You only have access to the ratio of the coupling square divided by the mass of the gauge boson. So you can get a first estimate of the mass of this new boson, for instance, if you assume that gauge coupling, the new gauge coupling, is of the order of the electric coupling. So if you say that G is of the order of the electric charge, E, then you get a prediction, from the measurement of this Fermi constant, which from nuclear physics is of the order of 10 to minus 5 in unit of the proton mass, so MP, so probably Gleb will use MP for the Planck scale, for me MP will be the proton mass. So that's just the experimental value, right? And if you assume that GW is of the order of the electric charge, you will find that the mass of the W should be around 100 of GeV. So that was the first guess estimate of where you will find actually new physics. Right? So let us now try to actually understand what could be really the physics that describes this new gauge boson, this W gauge boson. So what we have learned is that now you have an exchange here, you have a charge current, right? So you have a neutron that transforms into a proton by exchanging a W. Electron and neutrino. So this means since now the neutron has an electric charge 0 and the proton has an electric charge plus 1, necessarily the W in this diagram, okay, if all the particles are outgoing, the W should have an electric charge minus 1. And since it carries an electric charge, it should couple actually to the photon. The photon always coupled to every object that carries an electric charge. So you know, from this diagram, you know automatically that you expect actually an interaction between W and the photon. So this means that you have to deal with a non-abelian gauge interaction, because you have the gauge bosons that are interacting with themselves. Contrary to the photon doesn't interact with itself simply because the photon doesn't carry an electric charge. But if you have interaction or self-interaction of the gauge boson, this means that you have to deal with a non-abelian interaction. Non-abelian interaction. So, at this point, the question is actually what is this gauge group that should describe the interaction of the photon and the W, right? So what do you have at your disposal at the moment, right? You want certainly to build a theory that will describe let's say, the W plus and minus, just by the charge conservation. If you have the W plus, you should have the W minus, just for antiparticle, let's say. You have the photon. And what else? So you certainly want also to include the electron and the neutrino into an irreducible representation of this gauge group, right? Simply because they interact with the W. So the simplest thing that you can start, the non-abelian interaction that will describe those particle content would be, for instance, SU2, or you could think of SU1, 1, or you could also have E2 gauge group, right? An exception on gauge group. For some reason, actually, this is a non-compact group, so you don't have, finite dimensional unitary representation. So this was quickly discarded. Right? The same thing here. Actually, I think for E2, the only finite dimensional unitary representation actually is a trivial one. So it has only one element. So it cannot be describing also this particle content. So people then focused a lot on SU2, which was the simplest and maybe the minimal explanation of this beta decay. And this is actually what is called the Grojean-Glashow model. It's the first model, let's say, in '72, that were really trying to describe beta decay in terms of a gauge, in terms of a gauge, a normal gauge interaction.
Christopher, since you mentioned this E2,
yes.
Maybe you explain to the audience a bit details about this group, because I'm pretty sure that many people know what SU2 is and
yes.
SU11 is, but
yes. E2, well, I don't know. I don't know much about E2 myself. I mean, there is only the Dinkin diagram that, in this classification, in this Cartan classification of the group, there is this exceptional group. And I mean, people have looked at the representation of E2, and it has this particular property to the representation. I mean, I don't think you need to know the details. Just remember that it's a group of rank 2, so in principle it can really describe this particle content, but at the end of the day it doesn't really match with what has been observed. So what is the problem of Grojean-Glashow model? The problem is somehow that this model predicted actually some extra particle matter. Right? So in addition to the neutrino and the electron, you were expecting an extra particle, and this extra particle hasn't been observed. So why do you expect an extra particle? Simply because you want somehow the trace, the trace of the generator has to vanish, SU2 group. So here, the question, okay, SU2 is broken, certainly to U1, and the question is, that will describe the photon, and you would like to identify, let's say, the electric charge as one generator of SU2. So you can, for instance, choose your representation or your direction of SU2 in such a way that the electric charge is equal to T3, the third generator of SU2. But then you know that for any irreducible representation, the trace of T3 has to vanish. So the sum of the electric charge into the irreducible representation have to vanish. So now if you look at this electron and neutrino, you see that the electron has an electric charge -1, the neutrino has an electric charge 0. So clearly you see that there is something missing, actually, to make sure that the trace of the electric charge in this representation is vanishing. So this means that in the Grojean-Glashow model, you expect a new particle to actually complete this irreducible representation. And this should have an electric charge +1, 0 and -1. So that was the first attempt, let's say, to really describe nuclear beta decay in terms of a gauge theory. And the prediction of this Georgia-Glashow model is that you expect some extra matter. By consistency, of your description, you really expect to observe new extra matter in addition to what was observed or discovered before. So the alternative to this description is actually to assume that yeah.
Extra matter. It is X.
It has been called X. Yeah. X.
But you don't want to identify this positron, right?
No, because the positron is the antiparticle of the electron, right? So you shouldn't include both the particle and its antiparticle in the same time. So, that was the logical consequences of assuming actually that you have the minimal description of this beta decay. So minimal description means that the only interaction that I have at my disposal are really basically the W and the photon. So maybe at the end of the day, if this extra matter is not observed, maybe you have to challenge your first hypothesis and look at non-minimal model. So this means that you want to introduce extra forces. So that was the first possibility, no extra forces, but then you expect extra matter. And then the second possibility was to introduce extra forces. So clearly, the next thing that you can think of after SU2 is to add the simple U1. So you will consider SU2 cross U1. You will always go by step and try to increase the complexity of your model.
Christophe, excuse me, could one assume that this extra X particle is very heavy, and that's why it is not observed, or still the model is ruled out completely because of other reasons?
That was a possibility. Of course,
Is
the
still
splitting.
some possibility, that it's already completely out by some
I
other
think
reasons?
it's out because people have discovered the extra force, right? At the end of the day, also you expect that the splitting among this multiplet should be of the order of electric symmetry breaking scale, right? So you cannot push this scale. The mass of X arbitrarily high cannot be too much higher than the mass of the double. And this has been certainly well explored experimentally.
It means that it cannot be observed in high energy scale.
Well, it could. That was a consistent model, right? That could have been the description of nature. That would have given a fully consistent description of beta decay. Except that it seems that that's not the solution that nature has chosen. Chosen, instead of adding this extra matter, has decided to add an extra force. So now the question is how you want to embed the electric charge into this SU2 cross U1, right? So you could say, well, maybe the electric charge will be identified with T3 of SU2, right? But then you are left again with the same problem as before, right? So it doesn't work. Or maybe Q is actually the generator of the extra U1, right? That we call hypercharge for reason of it doesn't work either because in this case, since it's commute, then you will expect, let's say that the electric charge for the doublet here will have been the same. So you will have expected the electric charge of the neutrino to be equal to the electric charge of the electron, right? Simply because the two groups simply commute with each other. It's a direct product.
So it's a Taylor product or is a direct product?
It's a direct product. I don't know. For physicists, I don't know. For me, it doesn't make a big difference. It's a direct product of group. I won't make the difference between the group and the algebra, etc. So we lose the physicist. I don't care about this mathematical detail at this level.
But for groups, it matters.
For group, it matters. Yes. Okay, so that doesn't work again because the electric charge of the neutrino is different than the electric charge of the electron. Then you are left, with the possibility, which is actually that the electric charge is simply a linear combination of two generators, SU2 and U1. And again, up to normalization, which actually always differ in different books or different papers, you can always say that the electric charge is simply the linear combination of T3 of SU2 plus the generator of U1. And this actually works fine. I mean, you can now really classify all and derive all the quantum numbers of all the particles of the standard model and the SU2 and U1. I won't do it in details here. So, but one prediction of this model now is that you should expect actually an extra gauge boson. So extra forces mean extra gauge boson. That you can call the Z gauge boson. And this Z gauge boson actually mediates some neutral current. Contrary to the W, so W changes the electric charge. The Z gauge boson should actually mediate a neutral current. So in addition, let's say, to the neutral current associated to the exchange of the photon, you have an extra neutral current, which is just the exchange of the Z gauge boson. So, around the 70s or early 80s, the question was actually how to make experimentally the difference between those two possibilities. So people have tried to search for this extra matter. They looked at, at the collider experiment. They didn't find it. And then the next question was actually how to find this extra gauge boson. So you want to identify an extra neutral current, but the problem is how to make the distinction between the photon and the Z gauge boson experimentally. So you would like maybe here to identify the particle which is sensitive to the interaction with the Z boson, but which is not sensitive to, let's say, to the exchange of the photon. So you are looking for a particle, that doesn't carry any electric charge, but that will couple to the Z. And one obvious candidate is actually the neutrino itself, right? So you want to use the neutrino actually to prove that there is a Z boson, a new neutral current. So the idea was actually to look at the scattering of a neutrino against an electron. In order to prove this, you want to look at the scattering of an electron on a neutrino. And indeed, in this case, you have the exchange of the Z boson, right? So you have the neutrino here, neutrino. You have the exchange of the Z boson. Yeah, for some reason that I didn't have time to explain, people understood that there were more than one neutrino, right? Just by conservation of the different number of electron and muon, etc., they understood very well that there were more than one neutrino. Right? Because they knew the electrons, they knew the muon, and from that, they understood that there were at least two neutrinos. And then later on, people have understood that there is also a third one. That's another story. So here there is certainly a flavor index associated to the neutrino. Okay. So that's fine. So people try to look at this neutral current, but the problem is that here, for this interaction, you are also sensitive actually to a charge current. Simply, so this is, let's say, a T-channel exchange, but there is also a U-channel exchange, where this incoming electron is actually coupled to this outgoing electron via the exchange of a W. The electron here. Too many particles. is the exchange of a W. So this means that, okay, quantum mechanically you cannot distinguish the two diagrams, they will interfere, right? So you cannot, by observing this scattering, this scattering of amplitude, you cannot really say for sure that there is a new neutral current mediating this type of interaction. So you need to look at another interaction that will be only sensitive this time to the exchange of the photon, and where there won't be any diagrams mediated by the W exchange. And for that, the answer was simply to look at the scattering, this time not of a neutrino electron, but a muon electron, a muon neutrino. So mu on an electron going to mu on an electron. And in this case, since actually the W conserves the flavor, right, you cannot have this type of interaction. You're only sensitive to the Z exchange. If you replace here the electron neutrino with a muon neutrino, you're sure that this diagram doesn't exist, and you are left only with this diagram. So people now really try to observe this thing, and that was actually done in, I think, in 1973 by the famous Gargamel experiment. That was the first evidence of this neutral current associated to the exchange of the Z boson. The first experimental evidence really that there is a Z boson that exists in nature. So of course this is only a description at tree level. Actually at the loop level, at the quantum level, you could actually generate also this scattering by an exchange of a loop of a W. Make it here. So you start with a muon electron, W. The W will couple to the electron. Neutrino. Muon. So it's true that at tree level there is only this diagram that contributes. At the quantum level, you have also the exchange of a neutral current associated to the W. But of course, this is a quantum correction, and if the theory is actually perturbative, so here you are really trying to describe everything at the perturbative level, you expect really this to be subdominant compared to the tree-level exchange. So this means that really you can be sure by observing this reaction with a large enough cross-section, you can be sure that there is really a tree-level neutral current exchange. So that was really the experimental proof actually that the interaction, the dynamics beyond beta decay is actually described by this SU2 left cross U1 hypercharge gauge interaction. That's the foundation of the Standard Model. But of course, this is not the end of the story, because what people have learned in gauge theory is certainly that all the gauge boson is supposed to be massless particle. That's probably what Gleb is going to tell you at some point in this lecture, that gauge interaction need actually a massless gauge boson. And this was not the case, here, because we were always taking the low energy limit, so you were sensitive really to the mass of the W, so people knew that the mass of the W was actually important, just by this estimate, let's say that you were expecting the mass of the W to be of the order of 100 GeV, typically. Of course, people didn't really know what is the value of the gauge coupling, but a reasonable assumption was to actually expect a gauge boson of 100 GeV. So you have a gauge theory, SU2 cross U1, but this gauge theory has to be spontaneously broken, let's say, to a U1 hypercharge, electromagnetism, U1 hypercharge, and you need actually a description of this breaking of the gauge symmetry. And within quantum field theory, I mean, the way you want to describe this spontaneous breaking is via the X mechanism. That's the thing that was proposed in 64 by, different group, and the one that became the most famous is certainly Peter X himself. And it was, at that time, it was a simple, maybe the simplest example, so you always have to start with the simplest case, simplest realization, and if it works, then you are in good business. If it doesn't work, then you try to extend and go to the next to minimal model. So how do you want to break spontaneously the symmetry and give a mass to the gauge boson? Well, what you have to do is simply to introduce a scalar field, and this scalar field actually takes a vacuum expectation value in such a way that this vacuum expectation value actually doesn't respect all, let's say, the symmetry of your Lagrangian. So are you familiar with the X mechanism or not at all? A little bit, not so much. Okay. So, the way you do it is that you introduce here, in this case, a doublet, a scalar field which is doublet under SU2. So it belongs to a representation to the doublet of SU2, and it has actually an hypercharge which is equal to 1/2. Right? So as I say, the electric charge, is T3 plus the hypercharge. So doublet, so you expect a vector, so doublet is a two-component field. So you expect the upper component, so the upper component has T3 equal 1/2, plus the hypercharge which is 1/2, so you expect here to have a field which has an electric charge plus 1, and the lower component, T3 is minus 1/2, plus 1/2 for the hypercharge, so you have a lower component which is electrically neutral. So this means in particular that, this field here can acquire a vacuum expectation value, and this vacuum expectation value, since it doesn't carry any electric charge, will be left invariant when you're doing an electric transformation. So this means that if you manage to give an expectation value to this component of the X doublet, then you will break actually the SU2 symmetry to U1, SU2 cross U1. And this U1 that remains unbroken is really the electromagnetic transformation, is one that is written over there, the other black. And the claim is that this breaking, or if you want the vacuum expectation value of the X field here, is all what you need actually to generate a mass to the gauge boson. So how can you understand that? So first of all, I need to explain how you are giving an expectation value to one component of the X field. So this is possible actually if you write the potential for this X doublet. So you have to write something which is invariant under the gauge transformation. So it has to be invariant under SU2 cross U1. And out of the doublet you can construct a quantity which is invariant under SU2. And it's also invariant under U1 because it's just actually H dagger squared is just H dagger H. And if you want to put the index, the indices, so this is H, I, complex conjugate times H, I. I is 1 and 2 plus or minus for the two components of the field. So this is certainly an object which is gauge invariant by construction, and I can write the potential of this form, which is, let's say, the motional potential that you can write up to a constant, an arbitrary constant, but okay, if you're doing quantum field theory, without gravity, the constant doesn't matter. So I forget, and we will put all the constants in the potential to 0. And this is a motional potential that you can write, which is renormalizable, so up to operator of dimension 4. And the only non-trivial thing, if you want here, is that I made sure that, let's say, the quadratic term in H is actually has a negative sign, so it has a tachyonic mass. So usually if you write a potential, you will always write, for instance, m squared plus phi squared, right? Is the potential. with m squared being a positive quantity. So now, clearly, if you expand this, because of this minus sign, the piece which is quadratic in the field will have a negative sign in front of the mass there. So this means that the potential has really this form, right? So the origin is tachyonic. The sign of the quadratic piece is negative. So in such a way that the potential has no minimum, or if you want the origin, right, the origin, h equals 0, or h0 equals 0, is not a minimum of your potential, but is a local maximum. So this means that the origin is actually unstable. And the minimum of this potential is actually away from the origin, and will correspond to V. So when H0, here is H0, when H0 is equal to V, then you are reaching the minimum of this potential. So clearly, if you always want to sit in the minimum, so in the point of the configuration of field that minimize the energy of the energy density, then clearly the universe will end up into this point that breaks the SU2 cross U1 symmetry, and the only thing that remains unbroken actually is this U1 of electromagnetism. Okay? So that's the dynamics, let's say, that really triggers the breaking of the gauge symmetry to unbroken U1 of electromagnetism. So I say dynamics, I mean it's not really a dynamics. At this level, it's more like a description, because I put by hand this negative sign of the tachyonic mass for the X doublet. I didn't really explain what really the physics that give you this negative sign. I put it by hand. There are various types of dynamical models, that are really trying to explain why you actually have to have this negative sign in front of the mass there. But that's another story. That's physically on the standard model. In the standard model, you just describe electroic symmetry breaking by introducing by hand this potential. There are 3 parameters that describe the motional Lagrangian, which is renormalizable, and that leads to electroic symmetry breaking. Okay. So now you are giving an expectation value to the X field, and I want to tell you that actually this expectation value will automatically generate a mass for the W on the Z. And this is, again, the simple consequences of the gauge invariant of your Lagrangian. The fact that if you want a theory to be invariant under the local transformation, so here SU2 and U1 will be local transformation, so the transformation that you will perform will be different in every point of space-time. So that's what is called the local transformation, the gauge transformation. In order for the theory to be invariant under this local transformation, you need to promote actually the kinetic term of the X to a covariant kinetic term. So instead of the usual kinetic term for a field that will look like this, you will actually write a covariant kinetic term that automatically introduce some interaction between the scalar field and the gauge boson. So d mu h is a covariant kinetic term, so it's the usual kinetic term, minus some interaction with the gauge boson. So I say that it is a doublet under SU2. So you introduce the gauge boson of SU2, the generator of SU2, which are related to the Pauli matrices, so sigma A over 2 and H. And then it's also charged under U1 if hypercharge with an hypercharge minus 1 half. So the covariant kinetic term is something like that, B mu H. So this construction ensures that basically this kinetic term is invariant under the local transformation. Is it clear to everybody, or is it the first time that you see this covariant kinetic term?
No.
That's it. Okay, good. So So here the polymatrices, I mean for SU2, you know, you have three polymatrices. So sigma 1 is 1, 1, 0, 0. You have sigma 2, which is I minus I, and sigma 3, which is 1 minus 1. Then you have 4 gauge boson, right? So SU2 is dimension 3, so you expect 3 gauge boson. And U1 is dimension 1, so you expect a 4th gauge boson. And almost those 4 gauge boson will actually describe, you know, the 4 gauge boson that you observe in nature, namely the W plus and minus, the Z and the photon. So out of this 4 gauge boson here, to introduce, you will do some linear transformation in order to go to the mass against state basis that will describe what is observed in nature. So now you automatically see here that this covariant kinetic term actually contains a piece which is quadratic in the gauge boson. When you replace the X doublet by its vacuum expectation value, this is no longer a field, right? It's just a VEV. So this means that this d mu h squared actually contains a piece which is quadratic simply in the gauge boson. And a piece quadratic in the gauge boson is nothing else than the mass. So this means that you are really obtaining the mass of the W and the Z from the covariant kinetic term of the X field. So you can write explicitly this mass term, that's what I'm going to do. Right. So let us write in the vacuum expectation value, so I replace automatically this X by its vacuum expectation value, so d mu h in the VEV, in the vacuum, is equal to minus I over 2 so here I have W G times W1, so that's off diagonal. So the diagonal element will be G W3 mu plus G prime B mu. Same here with a minus sign for W3. And the off diagonal element is G W1 minus I W2 mu G W mu 1 plus I W mu 2 multiplying the expectation value in the vacuum with 0 V square root of 2. V square root of 2 simply because in the vacuum H0 is equal to V for the square root of 2.
And what happened to H plus?
Well, here in the vacuum, you can always do a gauge transformation in such a way that it's only H0 that acquires vacuum expectation. So, I mean, you cannot give a vacuum expectation value to H plus because this will break also U1 of electromagnetism. So you only want to give an expectation value to a field which is neutral under U1 of electromagnetism.
And we can do it.
Yeah, I mean, this potential is actually doing this, right? So the vacuum of this potential is exactly what you need. So now let us keep everything. So what is a Lagrangian now? The Lagrangian is 1/4, right? So you need to take the squares of these things. So 1/4. Okay, well, maybe I can do one more step, multiplying this matrix by this simple vector. So it's minus I over 2. So this times this times this. We have an element here, which is G W mu 1 minus I W mu 2. And V square root of 2, and the lower element is minus G W3 mu. norm of this vector. It will be G squared times W mu 1 minus I W mu 2. The norm, so W mu 1 plus I W mu 2 and V squared over 2 plus the other element, which is V plus 1/4 minus G W mu 3 plus G prime V mu squared V squared over 2. Now if you call this quantity W mu plus, this is just a complex conjugate, so that will be W mu minus. Maybe up to some normalization, so we put the square root of 2. And here, you can identify this simply as gauge boson up to normalization again, which is G squared plus G prime squared, square root of 2. It is just some linear transformation, right? So you want an object here to be canonically nominal, so you need to perform some rotation, so this will give you the normalization. So you see that this covariant kinetic term of the X field in the vacuum is simply giving you the mass term for the gauge boson, which is 1/2 G squared 1/4 G squared V squared times W mu plus W mu minus plus 1/8 G squared plus G prime squared Z mu Z. So here you obtain directly the mass for the W and the mass for the Z. So you have an electrically charged gauge boson with a mass mW squared, which is 1/4 G squared V squared.
Christophe, and V squared is the second term.
V squared, I forgot V squared. And you have the mass for the Z boson, which is again 1/4 G squared plus G prime squared times V squared. So here in this quarter, you have to remember that this is electrically charged, so there is not 1/2 in front of the mass, while for electrically neutral there is 1/2 times m squared times the field squared. And in addition, you have of course a massless gauge boson for the photon, and the photon is just the orthogonal combination of W3 and B, right? So in this case, the photon will be 1/square root of G squared plus G prime squared times will be G prime W mu 3 minus plus G prime B mu. So just the orthogonal linear combination to the Z. So that's really the spectrum that you obtain. Okay. So at this point, there is one thing that you can further compute from this spectrum, which is what is called the rho parameter, which is simply the ratio of the mass of the W divided by the mass of the Z, divided by the mixing angle that you need, or the rotation that you need to perform to go from the W3 and B basis to the photon and Z basis. Right? So you're performing a rotation. Right? So in this case, the rotation is simply cos theta W, cos square theta W is simply G squared. You can read off here, G squared divided by G squared plus G prime squared. So if you go, let's say you go from W3 and B, you go to the Z and photon by performing a rotation with an angle theta W. Okay? So you can compute this quantity. No? You have all the relation at tree level, are needed to compute these things. So the mass of the W is 1/4 G squared V squared. The mass of the Z is 1/4 G squared plus G prime squared V squared. And the cosine squared theta is G squared divided by G squared plus G prime squared. Going down. Clearly here, this quantity is equal to 1. So it's a phenomenological observable that you can compute. It's a prediction of, let's say, of the standard model, of the simplest standard model in terms of X doublet. Compute the raw parameter, and you find that it is equal to 1.
And what is the meaning of the raw parameter?
It's a mixing. It's a mixing between the original gauge boson on your Lagrangian to go from the to the gauge eigenstate to the mass eigenstate basis. This is really this rotation. So you introduce original gauge boson associated to the SU2 on U1 gauge symmetry, and the mass basis is actually obtained by a rotation from this original basis. So you compute and you find that it is equal to 1. Now there is a theorem in theoretical physics which is telling you that after a very complicated computation, if you find a very simple result like 0, 1, or pi, it means that either you have done a mistake in your computation, you screwed up a sign that gives you 0 instead of whatever, or there is a symmetry that explains why the result is simple. And clearly here, this computation has been checked many times and people didn't find any mistakes, so this means that there is actually a reason why the result is simple. So a reason in theoretical physics means that there is a symmetry. Physicists try to say that they understand something when they have identified a symmetry. So what is the symmetry behind this result? Well, this symmetry is actually an extra symmetry of this Lagrangian, which is not a gauge symmetry, but it's a global symmetry, which is called a custodial symmetry. That's a very important symmetry, that is usually not so much discussed in the book. When you read the standard model, people really insist on this local symmetry of the standard model, but they never discuss really the global symmetry, the global custodial symmetry. You will understand, as we are going to see in this lecture, this custodial symmetry is really important to actually understand the high energy behavior of the standard model. So how basically all these gauge bosons interact with each other, when you go to very high energy. Without the understanding that there is an extra global symmetry, of this model, you wouldn't understand actually this high energy behavior. So what is this custodial symmetry? Well, it's coming from the fact that, you started with a doublet, a complex doublet of a scalar field. And a complex doublet means that you have introduced 4 real scalar fields. So here it's 2 complex scalar fields. So the complex scalar field is actually 2 real scalar fields, with the real part and the imaginary part. And well, it's kind of obvious when you're looking at this expression, for instance, of the X potential. This X potential is actually invariant under the rotation among themselves of the 4 real components. So if you want, kind of obvious here, right? Here is simply H squared is simply H plus complex conjugate H plus H0 complex conjugate H0. So it means that it's really the real part of H plus squared plus imaginary part of H plus squared plus the same thing for the neutral component. Real part squared plus imaginary part of H0 squared. So clearly this expression is actually invariant under the SO4 symmetry. Right? You can really perform any rotation among these 4 real scalar fields, and the Lagrangian, in particular the potential, will remain invariant. So this means that this is a local symmetry of the standard model, and I have also a global symmetry, which is SO4. And actually SO4, just again for myself, SO4 is the same thing as SU2 plus SU2. At the level of the algebra is the same thing. At the level of the group there may be a difference in it, but at the level of the algebra, SO4 is SU2 left plus SU2 right. So what does it mean concretely, this SU2 left plus SU2 right? It means that actually you can, out of this doublet, you can construct a 2x2 matrix this time, where actually SU2 left will act on the left, and SU2 right will act on the right of this 2x2 matrix. This is just to show you that you can understand in very simple physical language, you can understand this mathematical relation between SO4 and SU2 plus SU2. So we'll construct phi, which is just I sigma 2H complex conjugate and H. So H was a two-vector, two-component vector. So now I add to this two-component vector, I add another two-component vector. So I obtain a 2x2 matrix. And the claim is that SU2 left will act on the left of this matrix, and SU2 right will act on the right. So phi will transform as G left, phi, G right dagger. For instance, okay, let's write the correspondence between, let's say, H dagger and phi. So phi explicitly, so here say that it's H plus H0. I want to write explicitly this 2x2 matrix. So I sigma 2 was 1 minus 1, right? So it should be minus H0 complex conjugate. Minus H plus complex conjugate, right? So in particular, you can see that the trace phi dagger phi, the trace of phi dagger phi will be simply yes. The determinant is a trace.
What you have denoted H squared.
But yeah, I don't need to take the determinant. I just want to say that phi dagger phi, phi dagger phi will be, okay, let's compute it explicitly. H0 dagger H H plus minus H plus dagger is H0 dagger H0 H plus minus H plus complex conjugate, and here if I haven't done any mistake, this will be H0 squared complex conjugate plus H plus squared, okay, this and this. Then the off-diagonal element will be actually vanishing, right? It's H0 H plus minus H plus H0. And here off-diagonal element is 0 again, And here the second diagonal element will be again H plus dagger H plus. H plus modulo squared plus H0 modulo squared. So you obtain that phi dagger phi is actually nothing else than H complex complete H squared times the identity matrix. So here you see, okay, so then if you take again the trace, for instance, you can say that the trace phi dagger phi would be simply twice H dagger. So you see explicitly here, for instance, that this will be now invariant of SU2 left plus SU2 right, right? Because if you perform a global transformation of this trace, right? So phi transformed this way, so phi dagger will transform as G right phi dagger times G left dagger, and then the trace of phi dagger phi will transform as a trace of G right phi dagger G left dagger and G left phi and G right. So G left dagger times G left is equal to 1, because G left belongs to SU2. And then by property of the cyclic permutation of the trace, you can put this G right on the other side, and again you have G right dagger G right, which is equal to 1. So this is nothing else than trace of phi dagger phi. Right? So what I've shown here is that really this potential, right, is actually invariant under this SU2 left cross SU2 right symmetry, which was obvious from the beginning because I said that it is invariant on SO4, right? So what I've shown in this description, going through this 2x2 matrix, is indeed that at the level of the algebra, SO4 is equivalent to SU2 cross SU2 left cross SU2 right. So that's the symmetry of the Lagrangian. Now I want to ask myself, what is the symmetry in the vacuum? So after H0 has acquired a vacuum expectation value. So again, I mean, as we have already seen, SU2 left is broken, right? And SU2 left combined with U1 of hypercharge to give you the U1 of electromagnetism. But at the level of the global symmetry, there is actually an enlarged global symmetry that survived in the vacuum. And this symmetry, this unbroken symmetry in the vacuum, as it is obvious in this expression, right? In the vacuum, so when H0 acquires its expectation value, in the vacuum, phi is simply actually equal to V over square root of 2 times the identity matrix. Right? The only thing that takes an expectation value is H0, H plus is vanishing in the vacuum. So in the vacuum, phi is proportional to the identity matrix. And obviously the identity matrix is invariant under this transformation, provided that G left is equal to G right. So in this vacuum preserves an unbroken global symmetry, which is G left equal G right. So you can use any SU2 transformation as long as you are performing the same transformation on the left and on the right, the vacuum will remain invariant. So this means that at the level of the global symmetry, this SU2 left plus SU2 right is actually broken to SU2 diagonal, or SU2 vectorial symmetry. Diagonal or vectorial means that you are performing the same transformation on the left and on the right. So that's a very powerful symmetry, right? Because you have really identified the symmetry of the vacuum. So in particular, you know, the masses that you have computed here, the masses should respect this SU2 diagonal symmetry. And since you started, with this W, this WA that were actually a triplet on the SU2 left, symmetry, they will also transform as a triplet under this SU2 diagonal symmetry. So this means that in the vacuum, you should find exactly the same quadratic term for W1, W2, and W3. So whatever, the expression for the mass, so you have a Lagrangian in the vacuum that certainly can be written as 1/2 m squared times W mu1 squared plus W mu squared 2 plus the mass for the Z, half mz squared, something that contains actually the W3, right? Because the Z actually contains the Z, so the Z goes on square. And the Z is cos squared theta W times W3. Plus a photon piece, plus a beam piece. But what this unbroken SU2 diagonal symmetry is telling you is that the quadratic piece in W1, W2, and W3 should be equal to each other. So the consequences of this unbroken symmetry in the vacuum is really that mw squared is equal to mz squared times cos squared theta w, where theta w is really the rotation that you need to perform to go from the photon on Z basis to the W3 and B basis. So you have identified this global symmetry, unbroken global symmetry in the vacuum that force actually this relation between the masses of the gauge point. And of course, this is nothing else than saying that the rho parameter is equal to 1. So again, this is not an accident, this is really the result of a symmetry, if you want.
You probably don't need 1/2 in the first term of your Lagrangian proposition.
Here I need 1/2 because I've written in terms of the
And you because of 2.
the real.
Yeah. Okay.
You don't need to put the 1/2 plus and minus.
Exactly. Right. Sorry.
It's always confusing, going from real to complex.
Yeah. That's right.
Can you please repeat why W1, W2, and W3 must be equal?
Well, simply because, there are a triplet representation of this SU2 diagonal. And since this is an unbroken symmetry, you should really find that in the vacuums, after the X has acquired its expectation value, you should see in the Lagrangian this explicitly, you should see this SU2 diagonal symmetry. And an obvious consequences of this SU2 symmetry is certainly that the quadratic piece for each of the elements of the triplet should be equal. Otherwise, the Lagrangian is not SU2 diagonal symmetric. Okay, is it obvious? Any question at this stage?
So this is the symmetry of the whole, this is the symmetry of the potential. But there are also countering with big scale this W. And is it also invalid with respect to the
So indeed, this is not an exact symmetry because this symmetry is broken by the gauging of U1 hypercharge. That will be an exact symmetry if you send the U1 hypercharge gauge coupling to 0. But it's kind of obvious here because I say, okay, I use a doublet representation of SU2, so doublet is pseudo-real, so that's why at the end of the day, I was able to combine, in a matrix, I was able to combine H and H complex conjugate. Why does it work here? Simply because these two fields transform in the same way on the SU2. A doublet is, SU2 is a doublet is pseudo-real representation of SU2.
Christophe, let me try to. There is some confusing thing in all this explanation. Because on one side, you have shown us that rho equal to 1
Yes.
is the precise quantity
Yes.
in the standard model.
Yes.
Now, what is the reason you are saying? Okay, the reason is custodial symmetry, but custodial symmetry is an approximate symmetry. So how approximate symmetry could be responsible for exact relation, which is 1?
Custodial
Including-
symmetry is exact.
Well,
The
no,
custodial symmetry is exact.
It's not exact.
It's exact.
in the standard
It is
model
exact.
before.
Is exact if you send in the limit where
In the
the
limit.
gauge coupling of U1 hypercharge is sent to 0. It's also exact in the limit where the top Yukawa is equal to the bottom Yukawa, which in nature is not the case.
Exactly, but rho equal to 1.
Rho equal to 1 was a prediction. Yeah, what was a prediction at tree level?
Yeah.
So now if you compute the quantum correction, there are some corrections to rho equal to 1. And this quantum correction, will be proportional to the breaking of the custodial symmetry. So those corrections that I haven't computed here will always be proportional to the gauge coupling squared, the gauge coupling of U1 times 1 loop factor, or they will be proportional to the mass difference between the top and the bottom, which is the difference between the Yukawa coupling. So that was.
May I make a group theoretical remark
Yes.
to your
Sure,
explanation?
sure.
You see, I think that this calculation of the squared of the matrix is exuberant. So if you just take the determinant of phi, you get h squared.
You get
And
right.
this transformation you have written, it confirms the determinant because both GL and GR are from SU2 and the determinants are equal to 1.
Yes.
So it's much easier to get the same result
Yes.
just
Right.
by calculating the determinant.
Yes.
Is the standard
Yes.
in the representation of SO4.
Right. Or the Lorentz group also you use. this
Yes,
system.
exactly the same.
Yeah, so here I really wanted, to use this to show basically that, you have something proportional to identity, but for the potential you can use the determinant in the sense. Trace of the square of the determinant. For a 2x2 matrix, they should be related to each other.
I think an important point is that your first column of the matrix phi and the second column of the matrix phi transform under the same SU2. You can get a local.
Right, absolutely.
That is
Absolutely.
important because the renders Lagrangian to be invalid,
Yes.
except U1.
Yeah,
The
yes,
does not.
absolutely.
And except you cover out.
Yeah, so here I haven't introduced the Yukawa coupling. I think you will find that the custodial symmetry is exact if the top and bottom Yukawa are equal to each other. Okay. Yeah, so one important consequences that we will explore in the second lecture this afternoon is that here, you have a breaking of a global symmetry. So you have SU2 left plus SU2 right, which is broken spontaneously by the vacuum to SU2 diagonal. So every time, you have a breaking of a global symmetry, you expect some ghost on boson. So in the limit of, let's say, when you send the gauge coupling to 0, you expect to see in the spectrum, you expect to see those ghosts on boson. So you expect, at least in the limit where G and G prime goes to 0, you expect 3 ghosts on boson, pseudo ghosts on boson. And these 3 ghosts on boson are actually describing the longitudinal component of the W and Z. So I need to give you an explicit counting of the number of degrees of freedom in the standard model, right? So let's do that. Is the right point to do this counting explicitly. And I will do the counting, before and after electric symmetry breaking, just to show that I'm not losing anything. Right? So it's just a reinterpretation of the degrees of freedom that are in the system. So before electric symmetry breaking, so when V is equal to 0, what do I have at my disposal? I have the X doublet. When I say X doublet, is at the end of the day 4 real degrees of freedom. Right? 4 real degrees of freedom. And what else do I have? I have this WA, and I have the B mu, W mu A and B. Right? So A is equal to 1, 2, and 3. So I have 4 massless gauge bosons. And a massless gauge boson has 2 degrees of freedom, 2 real degrees of freedom. So at the end of the day, I end up with 12 real degrees of freedom. And how these degrees of freedom rearrange themselves after electric symmetry breaking, and if you want after the X mechanism, so certainly now I have the W plus minus and the Z that are massive gauge boson. The massive gauge boson has 3 real degrees of freedom. We will explain that in a moment. So it's 3 times 3. I have a massless photon. So I have 1 times 2. And for the counting to be correct, so it's 9, 10, 11. So I will expect 1 physical remaining degrees of freedom, and this extra physical degrees of freedom is what is called the Higgs boson. So the Higgs boson is simply the fluctuation of the Higgs doublet around its vacuum expectation value. Here it's only 1. At the end of the day, I have 12. 12 degrees of freedom. So here the thing which is maybe not totally obvious is this longitudinal polarization of the W and the Z, or the polarization of a massive gauge boson. So what you have all learned, I think, in quantum mechanics is certainly that a particle of spin s has 2s plus 1 degrees of polarization. Right? That maybe is the only thing that you have to remember from quantum mechanics. 2s plus 1 polarization for particle of spin s or spin s. But if you have done some optics, this is in contradiction with the fact that the photon has only 2 polarizations, the 2 transverse polarizations. I'm sure they have all played, with laser and put some polarizer, and then you put 2 polarizer and you don't have any light after that. So you really have only 2 polarizations. You can get no light out of 2 polarizations if you put them perpendicular to each other. So the photon has only 2 polarizations, 2 transverse polarizations. So does it mean that the photon is violating quantum mechanics? Not exactly, because this theorem is true only for a massive particle. For a massless particle, actually, you can decouple some polarization. And that's exactly what gauge invariance is actually doing. So gauge invariance, we are talking about symmetry, but symmetry don't exist. I mean, there is no thing like a gauge symmetry. Gauge symmetry is just a way to introduce some spurious degrees of freedom that are not physical to make the theory invariant under this quote-unquote symmetry. But you're introducing some degrees of freedom that are not physical. You can always go into the unitary gauge, and in the unitary gauge, or after gauge fixing, etc., the photon will be described by 2 polarizations. So we are always excited about symmetry, but symmetry don't exist in nature. They are just the way the theorists are just write things to make it life easier and more symmetric, but they are not there. Right? You just bookkeeping. Yeah, space-time. The symmetry I think of space-time is different. Yes, that's true. But for local symmetry, internal symmetry don't exist. And even the global one. I mean, in string theory there is no global symmetry either. Which means that in a fully consistent theory of quantum gravity, there is no symmetry at all except the space-time symmetry. Okay, so yes. So for massless photon, indeed, you have two polarization instead of 3. And actually, if you think about it, this 2 versus 3 is simply consequences of special relativity. right? Because if a particle is massive, you can always go to the rest frame of the particle. And in the rest frame of the particle, there is no notion any longer of propagation, and the particle is not moving, so there is no momentum associated to the particle. So this means that there is no distinction between transverse and longitudinal. So this notion exists only when the particle is moving. Because when the particle is moving, you have the direction of propagation, and then you can say, well, there is things which is longitudinal in the direction of propagation, and there is direction transverse to the propagation. So clearly, if the particle is massless, you can never go into the rest frame, so this means that there is always a way to distinguish the transverse and the longitudinal direction. And if there is always a way to distinguish them, it means that actually you can always remove this longitudinal polarization. But clearly, for a massive particle, there is no way to remove this longitudinal polarization, because again, it's just a frame-dependent statement. If you go to the rest frame of the particle, you cannot distinguish longitudinal and transverse. So this is telling you really that special relativity and quantum mechanics is making sure that for a massive particle, you have always 2s plus 1 degrees of polarization and not 2s as for the massless particle. Now, I mean, this longitudinal and transverse polarization for massive spin-1 particle, have actually different behavior, which is quite interesting to look at in details. So what do I really mean, by this polarization? So again, you will do a plane wave decomposition, You will write A mu, A, let's say, as epsilon mu, that will describe the polarization. So it's a polarization vector, and then you have this, we can put also some gauge index, dA, and then there is simply the plane wave, kx, that describes the propagation of the wave. And this epsilon mu is just the polarization vector of the polarization tensor. And you have to choose a normalization, and this polarization vector is normalized to be minus 1. And there is one gauge fixing condition, which is that they have to be orthogonal in the 4-dimensional sense to the direction of propagation. So that's the polarization vector associated to a spin-1 particle. So now you can solve those equations. So for instance, you can put yourself into a frame where, let's say, k mu, a massive particle, would be E, 0, 0, and then the momentum of the particle, and those things are of course related by the Einstein relation that m squared is e squared minus k squared. So what are the solution of this equation? Well, there is two transverse solutions, two transverse polarization, but epsilon mu is really orthogonal in the space direction. So there is no time component, so it's 0, 1, 0, 0. Epsilon mu is 0, 0, 1, and 0. So clearly, you satisfy this relation simply in the space component. And it's normalized to 1, simply like this. Minus 1 due to the metric. Like I'm using a particle physicist metric, so convention is plus for the time direction, minus for the space direction. It's my metric. But in addition, I have an extra longitudinal polarization. One longitudinal A mu is equal to k over m, 0, 0, E over m. Right? So we say longitudinal because now this polarization vector has some component along the direction of propagation in space. Right? So that's why we call it longitudinal. But still is orthogonal in the 4-dimensional sense. Right? Because if you take the product of this, so it's E times K minus K times E. So this relation is satisfied. And it's also normalized to 1, right? Because if you take epsilon mu, it will be K squared over M squared minus E squared over M squared, which is equal to 1 or minus 1, thanks to Einstein. So you have two transverse polarization and one longitudinal polarization. And here you see, on this expression, you see the big difference between transverse polarization and longitudinal polarization. That the transverse polarization, you know, are constant whatever the energy of the particle is. Right? But this longitudinal polarization has some component which is growing with the energy of the particle. So this means that if you go into a frame, you know, where the particle is very energetic, you will have a very huge component to this polarization vector. So this means that at high energy, you know, somehow the only relevant degrees of freedom are really this longitudinal polarization. The transverse polarization remain constant, so they don't play any role. And if you go to very high, in a very boosted frame, actually only the longitudinal polarization will enter into the physics. And what we are going to see in this afternoon is that actually this longitudinal polarization is actually well described by this Ghost-Stone boson associated to the breaking of the global symmetry. So this is custodial symmetry, so the symmetry that survives the breaking of SU2 left plus SU2 right down to SU2 diagonal is really what will describe the physics of this longitudinal polarization at high energy. So that's why it's really important really to identify this additional SU2 right symmetry, this global SU2 right symmetry. Otherwise, you don't really understand the Ghost-Stone boson that emerge, and you don't see where they're coming from. Okay, so I think we can stop here the lecture maybe. And then this afternoon we will study in more details really the physics of this longitudinal polarization and try to see that you need, again, new degrees of freedom to have a consistent description of this longitudinal polarization.
Maybe some questions? Questions? Don't hesitate. If you like, you can ask in Russian, and someone will translate in English. If you don't like to ask in English, so ask in Russian.
Can you explain about introducing vacuum expectation value? Why? I see for water it's help us to do all these things, but why?
Why? I mean, I think it's really the understanding somehow that the symmetry of your theory doesn't have to be the same thing as the symmetry of the vacuum. I mean, that's something that you are always experiencing in nature, right? I mean, you know that the symmetry of space-time is invariant under rotation, but in nature nothing is really invariant under rotation. There is always one direction which is privileged, even on Earth, right? I mean, Earth is not invariant under SO3. You have really space, and the horizontal space, and the vertical space. So it's a spontaneous breaking of SO3 down to SO2. So the vacuum doesn't have to respect the full symmetry of your interaction, of your theory. So it's a new tool that you can play with, and what people have realized that this spontaneous breaking of local symmetry then generates a mass to the gauge boson.
This is the only way how to generate masses. You can pull them by hand, but it will
Yeah, okay, maybe we can discuss. There is in principle all the way, you know, that to make sense of a massive theory, instead of introducing, let's say, a spin 0 particle, you could introduce an infinite tower of spin 1 particle. And then again, you will have what we are going to discuss. I mean, the cancellation of this scattering amplitude. So the scattering amplitude will remain finite. So this means that you will have a consistent theory again at high energy, at least at energy above the mass of the particle. But yeah, the most economical way is with a spin 0 particle. And at the end of the day, I mean, it's nothing else than these counting degrees of freedom, right? And the massive spin 1 has 3 polarization, so you need somehow to acquire one extra polarization, and this extra polarization is usually coming simply from a scalar field. So it's really a scalar field that has been transformed into the longitudinal polarization of a gauge field. Somehow with in language that what we say that the gauge boson eats actually the Goldstone boson.
Let's continue after lunch.
During lunch.
And during lunch, please.